Hello there, thank you for joining me again today on the bench for demonstration, strip down for a look inside, as well as go through all the parameters and full features of a unit, including diagnostic calibration modes, which we'll look at later, and the internals and common faults and things like that. We've got a Marconi 2945 radio communications test set, very popular RF test instrument. These were used very widely in the 1990s and into the early 2000s. These came after the Marconi 2955 radio communications test set, which you'll have seen in other videos, but if you've not seen a Marconi 2955, then this is what it looks like. So this is the 2955B model radio test set that's been around for some time. That was the last one before the 2945, which we're reviewing today. But prior to this radio test set was this model of test set as well. Okay, so this is a really fully featured radio test set. I mean, back in the mid 1990s, just after the the demise of the 2955 radio test set from production, this was the bee's knees, out there. There weren't many other models in other manufacturers' portfolios which could really match this on specification and features. And what was nice about it at the time is that it was very advanced for its day. I mean, bearing in mind this was in the sort of mid 1990s, and these test sets continued production right up to the mid 2000s before they then were replaced with the other radio test sets that you'll see on my channel. But the very good features about these were the fact that they were so easily portable and movable from site to site. And indeed, the UK communications regulator, Ofcom, bought lots of these for use with their radio investigation service and radio communications licensing monitoring and things like that. So, they obviously invested heavily in these test sets. And the nice thing about these test sets as well is they had the additional features that the 2955 didn't have. For a start off, not only did they measure transmit, receive, duplex and the standard features that you find on most radio test sets, but in addition they were fitted with a spectrum analyzer, a tracking generator as well within the spectrum analyzer. They also had a transmit analysis function as well, so you could look at harmonics and things like that. So for example, under TX power, for example, you had narrow and broadband power measurements as well. You had DIR power as well, directional power meter, which meant you could use these kind of Marconi accessories, the same kinds of accessories that you use with the 2955 connected in the accessory plug. So that was nice. And then on top of that as well, under TX power again, they had harmonic analysis, so you could measure harmonics of transmitters, which wasn't possible with the earlier radio test sets. And then they also did transient analysis as well, so you could look at transmitter signatures, which was very useful in radio investigation work, in particular with Ofcom. And I think that's one of the reasons why they went to this kind of radio communication test sets. Indeed, there's a lot of police forces in the United States purchased these as well, because not only that, they also had the P25 modes on there, which we'll see in the systems, and in addition to that, they were very advanced test instruments for the day. So it was really a very fully featured radio communications test set. They did an avionics version of this as well, which was the 2946, and that had the additional modules and options fitted, which allowed VOR and IFR measurements to take place on aircraft navigational beacons or aircraft navigational radio aids. So they made the avionics version too. It was the same base fundamental internals and structure that we currently see, but it just had the additional modules fitted for VOR and IFR, etc. As well as that, this test set also had, as I say, the additional spectrum analyzer, the AF test as well, audio in-out test. Quite a lot of the features that you see now are modern radio test sets. but of course this was going back in the day in 1990s. This was very advanced for its day. Now we've got a systems menu as well, which is a very nice feature, and we've got different radio systems that we can emulate, and these are options that are fitted to these radio test sets. So you can purchase different types of radio network interfaces that are built in with the software. And the way this test set's designed is you could purchase the optional modules and fit them, and the test set microprocessor would auto detect the presence of that module and add the system automatically. So these were things that could be added by the purchaser later on, not necessarily needed to be ordered up front when you put the order with Marconi. So there was a lot of clever thought went into these, and they were very popular for that reason. Now, under the help menu section, we've got features as well for self-tests. We've got all the information about the serial number, what options are being fitted as well. We've got a diagnostics mode and a calibration mode, which I'll go into later. But indeed, we've got brightness control in 4-5 steps. We've got a rotary contrast control, so we can alter the contrast of the display. And the display is actually quite stable over its entire operating range. You don't have to keep adjusting the contrast, you can sort of leave it alone. Now as well as that, you've got the setup menus as well, so you can set it up to measure watts, dBm, the counter resolution. You can do the SINAD averages, as the RF power, external attenuator, so you can, you know, measure many hundreds if not kilowatts on the test set by using an external attenuator, and you can put that value in there. You can measure EMF or PD on the RF levels, and you've got a TX offset for particular radio systems that use a common offset between transmit and receive. So there's quite a lot to it really, a very, very capable radio test set. You've also got what appears to be the card setup, although this isn't fitted on this test set, but some of these test sets have a card reader here, so you can plug the standard Marconi radio card into the test set. Now if you've not seen a Marconi radio card before, that's what it looks like. It's just 512k, you know, nothing in comparison to modern day standards, and that would, you know, go in there. So that's the sort of memory capability, as well as having its own internal memories. You've got up to 10 memories internally that you can store. I'm not even sure if there's more actually. Let's have a look. Yeah, there is, I think. Am I right in saying that? No, I think there's only 10 memories you can have. You've got recall, you've got delete, store, protect, store, you've got store settings. So under store settings you can look at, you know, whether you want to retain that on the card or whether it's on internal memory. So you've got that feature as well, and really, you know, it's a very good little test set. You can select between scope and bar charts as well, obviously for your measurements. So it's up to you whether you measure, you know, bar charts for everything. You can auto arrange or bar chart select. You can go between the bar charts and auto arrange, or you can put in your own increment and decrement values as well. We've got all kinds of different capability regarding obviously TX frequency. We can input a frequency, or we can just leave it to auto tune. You can have RX equals TX as well, so whatever you've put in on the measurement, it will then replicate onto the other screen for the opposite receive or transmit measurement. So there's quite a bit. There's the AF gens as well, so obviously you can set up your audio gens for the AF gen output socket, so you can feed that into a microphone circuit and a transmitter and inject the necessary audio levels. We've also got different filters and things that we can assign as well under the mod meter, where we can measure AM, FM and SSB. We can change the IF filter between 300 Hz, 3 kHz, 30 kHz and 300 Hz. And then on top of that, we've got distortion and de-emphasis as well. So, you know, we can look at quite a bit there. Indeed, as well, we've also got tones which then allows us to do CTCSS, DTMF, digital coded squelch system, POCSAG as well, and then obviously we've got sequential. So under sequential, then you can select your different standards, and at the moment we're on CCIR, so you can define your own standard, or you can encode and decode as well, and you can select different standards, which in this case it supports CCIR, ZVEI, DZVEI, EA, user 1, user 2, so you can define your own, and then EIA, tone standards as well, so that's what it supports. So that's the transmitter side more or less, and of course on the spectrum analyzer as well, we've got another nice feature as well, which integrates really the functionality of the 2955R radio test set, which was a sensitive receiver model, or the 2955B with a sensitive receiver option fitted. That capability is also transferred into this test set. So we've got a look and listen capability where we can connect an antenna to the antenna port here, and then we can pull off air signals and listen to them, and we have a squelch and volume control here. So we can also set the span up just like we can in the spectrum analyzer. We've got different modes there, the different span widths if you like, predetermined if you like. We've got a different D mod, so we've got it on FM at the moment, we can switch that to AM as well. You've got de-emphasis, you've got 300 Hz to 3.4 kHz filter, a 15 kHz low pass filter as well, so they're all there as well, so you can really pull out noisy signals and filter out all the rubbish to listen to the content of those signals. And then we've got a tracking generator in the spectrum analyzer mode as well, so we can switch the Rfgen on and off, and we've got a track gen on and off as well, so we can put that on and obviously calibrate the ports between these two or just on that. So we can do all that capability too here, which we'll go into a little bit later in the video, showing that actually working with a filter as well. So that's that side. Obviously we've got the markers, we can set the reference, the scales, we've also got the span, center frequency, start and stop frequency, resolution, bandwidth as well. So, you know, again, a very nice spectrum analyzer, very useful, very, very useful. Under the AF test, obviously we can do what more or less the same as what the 2955 can do, which is by generating tones or a signal out on the Fgen out ports and then receive it back in on the inputs. So it's quite useful for audio work as well, not just radio communications work. Again, you've got the audio gen, you can set the different gen 1, gen 2s. With it having two generators on, you can change the shape between sine and square, and it will tell you what it's doing there. It's sin at the moment and then square. You can lock it as well. In addition to that, you can also set up AF filters, do distortion. There's also tones as well, so you can test audio circuitry within radios, such as the tone boards and things that are fitted to radios, to allow that kind of testing as well. So if we go on to the receiver side now, under RX test, again, you know, much the same as in the transmit test really. We've obviously got the Rfgen, the mod frequency, we can change the AF filters, we've got distortion, so under, for example, AF filters, you've got the usual speech band, 50 kHz low pass, 15 kHz and 4 kHz band pass. So you've got filters there that are not only band pass but low pass filters and speech band filters. Obviously we've got under the same menu distortion. Now under the distortion heading, then it breaks down into a sub menu, which is obviously distortion itself, SINAD, signal to noise and distortion, signal to noise and off. So SINAD, for those that don't understand what SINAD is signal to noise and distortion. That basically means that we take the received audio from a radio receiver and we connect it back into the AF input here, and in doing that, that audio can come from the loudspeaker or a headset or whatever. We can couple that away from the radio, feed it here. That will allow then the signal, which is the actual radio receiver's audio output being the signal, not the radio signal, but the radio receiver's audio output signal. Now what we do is we normally modulate that with a 1 kHz tone on the receiver, FM for example. If it's an FM radio, we generate a signal, radio frequency signal, we modulate that carrier with FM, so it frequency deviates, frequency modulates the carrier at 1 kHz tone at a particular level, normally denoted by the radio communications equipment service manual that we're measuring. And then what we do, recover that audio, feed it in here, and that's recovered 1 kHz tone from the radio receiver, and that measures that as a signal. The noise would be the receiver as you turn down the RF level, so that naturally in the service manual it may say, for example, it needs to be 12 dB SINAD greater than 0.3 microvolts. So you would then reduce the rotary control or type in the level 0.3 microvolts, whatever, and then the radio receiver, if it doesn't need too much alignment or work and it's in spec, it will produce a SINAD which is better than 12 dB. So in other words, it's proving the performance of the radio receiver. The poorer the radio receiver, the higher the RF level it needs in order for recovered audio to come out the receiver, for it to receive properly, audibly. And so if a receiver's deaf, for example, because it needs alignment or it's got a fault, and you need lots of RF level way above what it says in the service manual it should be getting, then naturally you need to adjust the radio receiver to get the best signal to noise. So essentially that's getting the minimum RF level that is possible with the least noise or distortion on the signal that's recovered out the radio. So the signal component is a 1 kHz tone, the noise is the crackle, hiss, pop and distortion that's on the radio receiver's recovered audio, and distortion is obviously how distorted that 1 kHz tone is as well that's coming out. So measuring three things there: the signal, the noise and the distortion. And that's one of the most common measurements that's used in radio receivers even to this day, is that particular mode is used and quoted many times in service manuals on radio alignments and repairs. And so if you had a specification that said it would be better than 0.3 microvolt at 12 dB SINAD, and you needed say 10 microvolts to make it receive at 12 dB SINAD, then there's something wrong with the receiver. It could be a fault, could be alignment, it could be a frequency, all sorts of different things, so you'd have to investigate further and repair it. Now signal to noise, SN, is just where it pulses the carrier with a 1 kHz mod. So it will turn the mod on for say half a second at 1 kHz tone, and then it will turn it off for another half second and turn it on. And what it does, it measures the period in which the 1 kHz tone is on and the 1 kHz tone is off, and then it can change it can look at the noise, the signal to noise ratio. So SN is also quoted in certain tests and specification conformance testing, so that's also another feature that you can do. And as well you can measure distortion, which is quite useful when even you have a good signal, a fully quietened signal coming into a radio receiver. Sometimes the output of the audio stage is distorted, and that can be down to the fact that the discriminator coil in the radio receiver IF stage needs adjustment. So instead of being a nice sinusoidal wave coming out the audio stage, it can be clipped or distorted. So that distortion measurement is also quite important in that capacity. Likewise, we've got tones again as well. So when we go into tones, we've got the same features again. We've got CTCSS, DTMF for example, where we can emulate telephone dialing tones, etc. Continuous tone coder squelch system, which is obviously CTCSS, encoder as well, and decoders. Then we've also got DCS, digital coded squelch, so they're there. And then not only that, we've got POCSAG, which is a paging standard used across Europe and across the world actually, and you can change the standards as well. You can put in your baud rate, your radio system's baud bit rate, mainly used for paging as well. This also emulates, which isn't found on a lot of other test sets as well, where you can test a POCSAG paging transmitter. A lot of radio test sets don't do that. They'll be able to use the radio receiver test on this to emulate a paging network, as we've just seen in the received side. But on this radio test set as well, you've also got POCSAG capability to measure POCSAG paging transmitters, which often isn't available on most radio test sets. It's normally just so you can actually test pages by going into receive test and then generating a POCSAG radio signal and putting a RIC, a radio identity code for a pager, and then send that as an emulation of the network. So that capability is also on the transmitter side, so you can measure your own POCSAG transmitter, which is great for if you're maintaining paging transmitters at Hilltop radio sites, or you're testing their encode capability. Under duplex test as well, where we can transmit and receive at the same time and test radios such as Hilltop radio repeaters or mobile repeaters, things like that. We can do exactly the same as what we did on both transmit and receive modes, as I've shown you previously, with the addition that you can switch between different antenna ports. So you can have transmit and receive on all the same port, which is the high-powered N-type, or you can have the input signal on the N-type from the transmitter, for example, and the receiver on the low-powered, obviously, BNC socket here. Or, for very low-powered applications, you can use the antenna as the transmitter input, but it's got to be less than 1 watt, otherwise you damage the instrument. And then you can use the BNC as a receiver, or you can do it the other way around, where obviously you can use that as a transmitter, this is a receiver, and then back to where we were to start with, which is everything on the N-type port. Now, talking about the duplex side, obviously, and when we're also making transmitter measurements, this port here, the N-type can take 150 watts as well, so that's also a nice feature. It's quite capable of taking 150 watts continuous. I do believe it can even take even more momentarily as well, so that's pretty good for SSB transmitters and things like that, that can often give quite a high output level. The nice feature as well about the spectrum analyzer, if we go into systems and spectrum analyzer, we'll go into systems first. Under systems we can select no system or system, but then of course we've got different modes here. So in this particular scenario we've got no system, we've got PMR, AMPS, TACS, which are cellular analog systems from the 1990s. This system here I think is a European standard, and then MPT 1327, which is trunk radio networks, which were widely used at some point, and I think still are in many applications. And you can install options on there as well, and systems, you can go into that. There's an unlock procedure you can go into, which is in the service manual, and they can enable systems as well, because they're all on there, but you just need to enable or disable them apparently. So yes, there's all those different systems. Under spectrum analyzer, obviously, we went through that earlier, and then on the AF test side we've been through that as well, so we've covered all that. Now on the oscilloscope side of things as well, another nice feature on this, which again is still on the 2955, is that you can have the AF input coupled AC or DC, so you can use it potentially up to, I think it's about 30 volts or 40 volts, something like that, DC or AC coupling there, so you can turn it into a little voltmeter. We've also got single and repeat mode buttons for the oscilloscope as well, so we can adjust the position of the center line on the oscilloscope. So we've got that capability. Now to expand on that as well, we can obviously change all the levels that it's measuring and frequency as well, so and the time period, so that we can analyze a signal as well, which I'll show in a moment when we do some radio testing. Now as far as RF levels concerned, on the Rfgen output, You can control that obviously by the rotary control. You've got frequency up and down buttons here, which you can set with the increment as well. In this particular case, all the blue keys represent the modes of operation. These keys just deal with what's on the edge of the screen for the menus. The orange keys are basically things like the sub modes, frequency, you've got level, all sorts of different features there, plus as well megahertz, kilohertz, hertz, that kind of thing. And we've also got, under the help menu as well, we've also got help itself. So if you're unfamiliar with doing any testing, for example, of radio systems, then it will give you guidance by selecting these different modes. So that's also quite pardon me, that's also quite useful. So there's quite a bit to it really. So what we'll do now, we'll do some radio testing with it, just to demonstrate it being used with a radio transceiver or a signal generator, and then we can then look at the internals of it as well. Well, one of the things as well that always disturbed me about these test sets, considering the effort that went into making them as fully featured and as popular as can be for purchasing for businesses that were into repair and maintenance of radio communication systems, is round the back there isn't actually a VGA output for an external monitor, which is always a little bit disappointing. And that's the loudspeaker there, so you can hear the audio coming out the test set when you're dealing with the audio measurements and things, or off air receiver. So round the back really, I was expecting when I first had one of these many years ago for it to have had a VGA output port on the back, or at least something so you could couple composite video out, but there's nothing. So unfortunately that's one of the problems with these radio test sets, as well as the LCD screens fail on them, and they're a devil to fix. I've successfully repaired about 70% of failed LCD modules. It depends on the age of them. They're so delicate and very easy to damage further as well, and they're no longer available as a spare part, which makes it even worse. So that's the only thing at the moment that I'll say about these test sets that I don't like, is the fact they haven't got a video output on the back. I'm sure that you know, there will be people out there that can hack something together to make it possible, but it's a shame it wasn't fitted as standard. On the rear, the back here, we've got down there, if I can just jack it up just so that we can see under it, because it's odd position to put things. They've actually got a, just here, that's a external mod. That's what that is, external mod in, and then next to it in the middle we've got a demod out, and then to the far right is a frequency standard input which accepts 1 megahertz or 10 megahertz, and then we've got the usual 9-way serial port, a voltage selector switch for the DC input so you can power it from a battery, and you can also charge a battery depending on what position this rocker switch is. And then obviously the GPIB port as well, if that option's fitted. Some don't have that option, so it could just be a blanking plate. Again, something that I've always not liked about Marconi test sets when they got to a certain age is the fact that they have a rocker switch on the back. Now that's great if there's just this piece of test equipment on the bench and nothing else. But if you've got this stacked along with other pieces of test gear and it's wedged into a bench, or you inset it into a bench or something like that, you can't reach the power switch on the back. It's very difficult to reach around the back and get to that in those circumstances. And I've always been a bit disappointed that they never had the power switch on the front. And it was a design methodology that they continued as well onto the 2960 series radio test sets, which, you know, are these test sets here. Again, rocker switch round the back, and having to reach round the back to try and switch them on, you just can't do it. So I don't know why they did that. It was a bit silly for me to for them to do that, and it's awkward, but there you go, that's just how they've designed it. So we'll do some measurements next, and then we'll see how we go with that. Okay, so we've got our trusty little radio connected in to this port here, and we'll just do some transmitter measurements as well, and DTMF checks. So if I key up, for example, onto that now, we'll measure the transmit power, which we can see there. 1, 2, 3, 4, 5. So doing 4 point something kilohertz deviation. On bar charts, now it measures the positive and negative sides of the waveform too, not just like the oscilloscope does. The oscilloscope looks at both positive and negative side as well, but the bar chart will tell you. We can obviously pull that apart. 1, 2, 3, 4, 5, and then compress it a bit as well. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, 1, 2, so we can see the speech. But the bar charts themselves are quite useful because just like in the oscilloscope mode, it'll tell you what the plus and minus is as well, so you know if your modulation circuits on your radio are not working correctly. So we can test that. 1, 2, 3, 4, 5, 1, 2, and then of course we can put different speech filters in as well. So we've got the under mod meter filters. We've got the different filters in for the IF range as well, for using with different transmitters. On the AF filter we've got the speech band, so only the speech is looked at between 300 Hz to 3 kHz, and then as well as that we've got a 300 Hz low pass filter as well, so that we can also have a look at the transmit CTCSS if we needed to look at that. So there's quite a bit there. As well as that, we've got the transmit analysis as well under TX power, so we can look at harmonic content of a transmitter, for example. So it will tell us the fundamental frequency and power. It will then tell us the second, third, fourth and fifth harmonics, what their level is. And as well as that, we can go into transmit analysis as well, so we can arm it, and this will measure the signature of a transmitter. So that's me keying up there, and every transmitter's got its own unique signature. So this is one of the features that Ofcom, each time I key up, you see, you'll notice it's the same signature that it starts with. And as I was saying a moment ago, every transmitter has its own signature. So this is one of the reasons why the communications regulator here in the UK, Ofcom as it was known, or the Radio Investigation Service of the Department of Trade and Industry's Radio Communications Agency, which was the predecessor to Ofcom, they purchased thousands of these radio test sets for all their radio investigation teams around the UK. So it was one of only a very small selection of radio test sets on the market at the time. I think Roden Schwartz did something similar, where you could measure the transmitter signature as well. So it was a very useful feature for radio investigation work in finding interference sources, abuse of a radio spectrum, that kind of thing. So the radio test set was purchased by Ofcom for that, and they recently sold Ofcom hundreds of these radio test sets from one of their transmitting sites down near London. But I always found that quite useful, that it was, you know, it's just a nice little feature. And obviously you can set up the different modes. You've got the reference level as well, so if you're looking at very weak signals even off air through the look and listen function, you can see the transmit signature. So it's a very good monitoring capability when coupled with look and listen under the spectrum analyzer, which we'll look at shortly. Obviously you've got the marker as well, so you can shift the marker about. You can manipulate markers to where you want them to be. You've also got trigger levels. You can plus or minus trigger it, or obviously pre-trigger the system and set it for a certain threshold. And then of course you've got TX frequency as well. You can input different frequencies in, and you can obviously you make it, when you look at the analyst of the signal, look at the detail in more precise terms, as opposed to you know, so you can shorten that or lengthen it out, and then you can get the unique signatures, you know, so you can get quite forensic with it really, in looking at that signature waveform on different transmitters. Obviously the under TX power as well, we've got broad and narrowband power, so you can look at a transmitter's narrowband power measurement. So in narrowband mode at the moment, this is producing, according to that, 8.32 watts, but in broadband power, then it's wideband power, it's 13.3 watts. So that's there too, you know, you can look at that. The DIR power, I'll just turn that down. The DIR power is where we use that accessory, which is hiding away down here, this Marconi accessory. Now that Marconi accessory also works with the 2955 radio test set as well, and that just plugs in here into the front. So we can take this Hilltop radio sites and measure Hilltop radio transmitters, antenna performance on the radio towers, such as forward and reflected power, VSWR, all these parameters can all be measured as well. So that capability extends it into maintenance of Hilltop radio towers, antenna and transmission line systems. Under the AM principles as well, in SSB, we can measure peak envelope power, or CW. So now press the button, it says PEP. So that's useful for AM and SSB. And then CW. So we'll have a look at the spectrum analyzer next fully. Okay, so what we'll do now, we'll just before we go on to the spectrum analyzer, back under transmitter tests and tunes, we'll just have a look at the by the way, you can also set when you're on the antenna port here, when you're looking at external radio systems off air from further afield, you can then also scrutinise their signalling tones as well coming off, and you can set the RF thresholds here of the signal level coming in to the antenna ports before it starts analysing. So that's what this is here, receiver input level. But if we just look at, for example, DTMF, oops, press the wrong button, return, tones, DTMF. So basically on this one, just make sure I've got my filters on as well, so I did faff about with those. AF filters, we'll put a 15 kHz on, mod meter, AF filter, 15 kHz low pass, right, okay, so we're getting everything then. Right, so if I go back into tones now and then select DTMF, I can now key up the transmitter, and then as we key it up, I can obviously press buttons on here and then listen to the audio. Move channel. Oh, I think I've changed channel. That's what's happened. I pressed the button on here and it moved channels. So now we're on 77 now, 433 megahertz. Right, tones, DTMF, and now when I press the button on here, it's recognising the DTMF tones, you see, that are coming in. So that's quite a nice little feature. As well as you can emulate those going out as well on the receive side. So that's just a little brief overview of the DTMF signalling capability of it. Okay, so on the spectrum analyzer function, we can obviously keep the transmitter here. We can just see some minor changes on the carrier there, because obviously we're looking at very narrow span. Let's try 100 kilohertz. 5, 1, 2, 3, 4, 5, 1, 2. So you can see the modulation of the frequency deviation of the carrier. I'm not sure if 20 kilohertz is available. Let's have a look, see what we can get down to. Right, 870, 60. So that's like 60 kilohertz. 1, 2, 3, 4, 5. So you can resolve quite a narrow span. We'll put that back at 100 kilohertz. Radio test 1, 2, 3, 4, 5. And the no mod at all, it goes back. Now, excuse me, as part of this we've also got the marker, so you can move the markers about, and so basically on the we can adjust the attenuators with these buttons here, so we can obviously get that carrier way down so we can measure it properly. We've got the marker to reference as well, so you can adjust the marker, and again you can change that using the rotary. You've got the reference level as well, so you can set the reference level and the top line. You've got the center frequency, the span, start and stop frequency for the track gen, which we're going to look at shortly. But then one of the other little features as well that I quite like on this test set is that it's got this look and listen capability. So right now it's on as a look and listen, and we can use these level keys then to make the sensitivity of the receiver. So we can, for example, I put a center frequency in the broadcast band, so 98.9 megahertz for example, and then we select the antenna, which is this port here. That's the input port, and then we can now begin to pull out those broadcast signals. So this is a broadcast signal. I can obviously then make that say 10 megahertz wide, and then we'll be able to pull out oh, I'll change the center frequency, haven't I, like an idiot. 98.9 megahertz, and then the span I want 10 megahertz. No, I don't know what I'm doing wrong. Let's have a look here. Center frequency 98.9 megahertz. Span, see, predetermined span under look and listen. I was trying to enter something in manually and it doesn't like that, so that's like a 1 megahertz span. 500 kilohertz, 200 kilohertz, 100 kilohertz. So you can really scrutinize things, and then we should be able to hear the audio. There's demod. Kilohertz. Center frequency 101.1 megahertz. So we can listen to any radio signals then coming off air. So that's quite a nice little thing. Let's just have a look at resolution and bandwidth. listen off. So as well as just having look and listen capability as well, you can actually, back in spectrum analyzer mode with this antenna selected here, you can actually go and adjust your span anyway to say 100 megahertz in this case. So then we can have a look at the radio spectrum. At that centre frequency 100 megahertz, 100 megs, so 50 megs either side. We could even make it 500 megahertz, in which case it'll take a little longer, but it'll resolve that. So anything in the radio spectrum now between 200 megs in the middle, so basically 0 to 200, 200 to 500. Just trying to see if I can get these markers to appear. So span 1 megahertz. Right, marker. There. So we've got this little line here, which is the marker, which then obviously reads the dBm level here as we get on the signal or come off it. So that's how you can measure that. And most instruments I come across, it's like a bouncing ball that you can move about, but this is just a very fine line. It's quite difficult to see this fine line, but at least it's there. Okay, so for the trap gen side of things, we'll look at that next in conjunction with the filter, I think. We'll just show that functioning, and then you can see that going as well. Yeah, just a bit more on the look and listen thing. I found the radio signal here on about 164 megahertz, 0.225. So there's some kind of data channel. So again, we're off this antenna here, this whip aerial, and we've got maximum sensitivity, I think. Yeah. So, but again, we've got two sidebands here on that particular mode. So if I move the wharf there into the next one, so that's sending some kind of data out. So I put squelch on. So if I change the span, under look and listen mode, the span's restricted, you see, to these 4 selections. But if you come out of look and listen mode, if you switch look and listen to off, then you get the you can alter the span to whatever you want. Then you see, you can put in your own. So I found that there's some other signals up here. I was just looking with the centre frequency, because I saw that one there, and there's some more. That one's quite a significantly high one. There's another one just there. But of course, back in these days, you know, this is like a band scope thing. It was brilliant, you know. Of course, today we've got the modern SDR software-defined radios that can, with waterfall band scope, they're fantastic, you know. But this is a proper calibrated spectrum analyzer as well, so it's not a toy sort of thing. We've got some more signals here. Let's just have a look at this span. We'll make it 10 megahertz and then see what that's like. These look like tetra channels, maybe not though, 179 megahertz. So let's make it 1 megahertz now, the span. So we're getting some signals here. Center frequency, look and listen. Let's see whether we can hear them. So if I just move that, I'm not sure if we can hear them. Yeah, there's a carrier there or something. Probably just interference. Probably just interference in here, to be honest with you. So if I go back to look and listen off, then span, and then make it 10 megahertz again. Center frequency, and we're nearly at 200 megahertz there, 181. There's something there at that frequency, 190. The 200 megahertz frequency range in the UK in the 1990s was all the National Band 3 network, as it was called at the time. That was an MPT 1327 trunk radio network. The railways were on it as well, and before GSMR came out, railways. Look at this. This is definitely something of interest here. 200 megahertz. This will be digital audio broadcasting, DAB. That's what that is. They're the multiplexers for the digital audio broadcasting and what have you. So they're quite powerful. Won't be able to hear what's on those, obviously, because of the digital codecs. We've got some more multiplexers, and for DAB, national radio, 220 odd megahertz. So that's where National Band 3, or Band 3 as it was known as in the UK, for trunk radio networks. When it went bust, the radio frequencies got bought out by or sold off by the communications regulator. Got something there that looks quite interesting, 242 megahertz. So we'll have a look at that. So what we'll do, we'll switch to look and listen, and we'll see what we can hear on that one. Center frequency. I can hear something, but just sounds a blank carrier. Might be some video information on it, something like that. I can listen off. Center frequency again, and start tuning round. Keep going up the frequency, 250 megs nearly now. It's got one or two little signals coming through, not much at the moment. So something there, not sure what that is. Looks like it's jumping up and down at 270 megahertz. You can listen. Another blank carrier. So it's interesting, you know, going up and down the frequency bands and things, seeing what's on at a glance. You can, you know, you can pick things up and listen to things. So there's all sorts of interesting bits and bobs. Span, we'll widen the span again. We'll put it something like 100 megahertz this time, and then we can will it allow 100 megahertz? I would have thought it would. 100 megahertz. Yeah. So there's a little bit going off center frequency. So there's not much at the moment that I can pick out in here, because where I am it's quite bad with internal radio signals. I think this here is Tetra coming up, 380 megs. So this will be the Tetra radio systems that are out there, and so on and so forth. So that's a little rundown of look and listen anyway. Okay, so I just wanted to show it working with this Marconi accessory. So what we're emulating now is we're feeding the transmitter instead of into the test set. We've set up this what is the Marconi directional power head. This particular one works from 25 to a gigahertz, 25 megs to a gig. But I've got others that work from 0 to 30 megs or 50 megs, so that they cover HF. Now these can measure up to, I think it's about 400-500 watts as peak envelope power, something like that. So they're quite high powered rating. But we've got the transmitter connecting in here into the what is the directional coupler input port, and then the antenna, what would be a makeshift antenna, which I'm using an RF attenuator here that's got an open end on it to simulate a reflected signal. It will allow so much of the signal to be matched into the internal load, but also reflect some back, because we're leaving the output port open-ended. So what we'll do now, we've connected it into the test set. On the 2955s, well, no matter what screen you're in, when you plug that in, the test set automatically recognises it and would then switch to this screen. But it doesn't do that on the 2945s. You've got to go to the DIR power, which is under where it says TX power here, and then you've got DIR power, which is this option, and that then takes you into this screen. So when I key up the transmitter, for example, on there we'll see the forward power, which is at the top, which says 10.7 watts. The reverse power is 1.8 milliwatts, and then the VSWR is 2 to 2.6 ratio. So that's obviously the VSWR. If this was an antenna, you want the VSWR as low as you can possibly get, so you don't get the reverse power, reflected power, which in this case is 1.46 watts. So that will be our system losses being returned back to the transmitter. The higher VSWR, the higher the reverse power will be, and the more damage you can cause to a transmitter. So that's an example of that. Obviously you can improve the you've got bar chart select, so you can go between these, and then you can alter the ranges yourself manually, or have auto ranging. Again, you can do the same with that. You can get down into granular detail basically on the levels that it's measuring, and obviously on VSWR as well you can do the same there. So you can go down into whatever units of measure you want, and get down into some more granular level. So it's quite handy, a little feature, to have that. And again, we've got peak envelope power and CW. Moment it's in CW, but under peak envelope power it measures AM and SSB transmission, so that's quite handy as well. So very nice little instrument, lots of nice little features, that are quite useful. So that's an example of it working with the Marconi directional power heads, which seem to work across most of the radio test sets that Marconi offer with this kind of accessory, this DIN socket arrangement on the front. So just before we go on to receiver test, I just want to show you the self-test feature within the test set. Now this can be a little bit of a problem for these. I think the way they've designed the software on them is that if you've been to other settings prior to doing a self-test, it somehow affects the self-test. If you change the relays on the antenna selections of these BNC and N types, you've got an Rfgen signal already being set up for coming out of it, that basically sometimes it'll fail its self-test, and that's because it's relying on you being at the default factory level reset, which is memory 01. And when you recall memory 01 or whatever, and not the Rfgen off and other things that you've got, it'll always pass the self-test. There's quite a lot of people have problems with the self-tests on these. Generally speaking though, it should pass them all without failing, but sometimes when you manipulate some of the settings on the test set before running the self-test, if you haven't put the factory default factory preset settings recall 01 in, then it may fail on some of the tests, and that's not because there's a fault with the test set, it's because you've had it on different settings prior. And the way they've written the software on this test set means that if you go straight to the help menu and then select self-test without doing the reset, if you like, the factory default settings, then what happens is then you'll start seeing certain things fail. But after you've sort of sorted everything out with the settings and everything and come back and then run the self-test again, it'll pass them all. So don't panic if you do see, if you're interested in buying one of these and you do a self-test, just do the memory 01 or default the service monitor TX. Make sure that the antenna ports are switched off from these BNCs onto the N, and the Rfgen for the receiver switched off. Then go back into the help menu, select self-test, and then click go, and it should race through them. It goes through quite quickly actually at testing all the parameters. As you can see, it's rocketing through. It tests all the RF attenuators, a broadband power mod, all that kind of thing. AM and FM deviation and depth, and then at the end it'll hopefully give a full pass result right the way down. But just to demonstrate, sometimes if you're not set it up properly as per the instruction manual, so for example you can go to receive test, it'll change these ports for example sometimes, you know, depending on what test you were on before, and then you go straight to because the Rfgen's on now, you see, it's sending a signal out as well. So then if you go to self-test and then do go, then it'll start failing things, and of course what happens is sometimes it doesn't do it, sometimes it will. It's a bit of a software glitch on them. I don't think it's so much how you've operated the test set prior, it's just that it doesn't take into account the current configuration. It's a bit hard to explain. I'll see if I can get it to fail, but normally when you got the BNC and that on and then run the self-test again, potentially it could do it, but it's like a setting that you've done prior and then it will fail. It's not doing it, but I have seen it happen, and it is a known problem on them, but it's not actually a fault on the radio test set at all. It's the way the software is written for the test mode. So it's just one of those things. If you do get that happening to you, then don't worry, because obviously it can panic some people. So the Rfgen level's off at the moment. I think it's when that's on, actually. I think that's the on-off button. I think when the Rfgen's on, and then you go there, and then select self-test, what it does, it interferes with the test results, because the Rfgen's on, but it's calling me a liar. But you might get that happen. It sort of happens every now and then. It's nothing to worry about, but if you do test one, just do the memory 01, the factory default, restore it back to factory defaults and then run the test again. You'll probably find it'll just all pass. Obviously if it repetitively fails on every test, then there is a problem, not naturally, but you've just got to be open-minded that it could be whatever settings it was on prior, and then you run a self-test and it might fail, and then you come back and do a memory 01 and then default it back to factory default and then do a test again and it all passes, and you're sort of scratching your head. There's a lot of people contacted me in the past about that problem, and it is a widely known issue. I think when these were IFR branded, after IFR took over Marconi Instruments, I think they did a software update on them, a firmware upgrade, and I think that took care of that problem. So it's just for information really. As you can see there, the test set's fully functional. So that's a little rundown of the test modes. Okay, some receiver tests. We've got obviously the usual, putting the radio frequency level. You can switch the Rfgen on and off, mod level as well, setting up your mod level. I've just left that at 1 kHz, 1.5 kHz deviation. You can also put on filters. You can do what you like with that, but basically if I just switch the Rfgen, I've set the frequency for 33.5 megahertz, and then we'll just switch the receiver on, the Rfgen on, and then on the radio ourselves you can obviously hear the 1 kHz tone. Now I can change that Modgen 2 excuse me, and I can change the frequency increment if I wanted to 100 Hz, and then when I press the frequency I could do that. But for the test that we'll be doing for receiver specification, we need the output of the radio receiver connected into the AF input port. So we've got a lead here which is a BNC to 3.5mm jack plug for the audio, so we'll connect that in. So we'll just put that into the AF input on the test set. Now on the back of the radio there is a socket just there, so we'll plug this other end of the lead. It's always difficult working one-handed, but there we are. We've got the audio lead in now. So technically, in theory, I should just be able to shove that under there and get the audio output now from the receiver. So we're already getting indications on the bar chart at the level of, obviously I can test the AF output of the radio receiver by turning the volume up to maximum, so we can look at the audio PA stage is producing the right output level, and obviously we could put an 8 ohm load in parallel with that to simulate a speaker load and then measure the signal as well, so we can even do that on the AF tests. So I'll just wind it down to about 1 volt, and then we can turn on the scope, the oscilloscope, and then we can adjust the levels, so we can close it down a bit, and we can also look at that further. Now, as you can see there, we're now coupling what is the receiver audio from the radio receiver into the test set, and we're analysing that there. Now we can then connect up our next measurement, which is signal to noise and distortion, which is SINAD. So I can select that. Now it's going to give us a SINAD reading here. So for example, we can now spec test the receiver by going to Rfgen level, and the service manual probably says something like 0.5 microvolts for 12 dBs or better. So if we do, for example, 0.5 microvolts, I think it's that one, yeah, and then the SINAD is 32 dBs. Now if we turn the volume up of a test set, and then we turn this level down, because the test set's now monitoring this part, because if I remove that, there's no audio obviously. So the test set's monitoring that now, and we're generating a noisy signal. So if I get the SINAD down to about 12 dBs, let's see what it's 16 dB. It's about there, I'd say, roughly the averages. 0.1 of a microvolt. So naturally, you know, if we were getting that level of noise that we had there, when we've got such a high level of signal coming in, then naturally the radio receiver has got a fault on it, or it needs retuning. You know, if a signal got lost all of a sudden, and you needed a very high RF signal, I can simulate that by actually having a very loose RF connection here on the front. So if I turn the RF level down now, so we're getting down to that 12 dB figure nearly, and we're at 6 microvolts. So naturally, if and then it'll start to squelch out there, 5 microvolts. So if that were to happen when we got that properly connected, obviously, this is just to simulate a fault condition, then we would have a problem, because, as you know, the service manual will say 12 dB SINAD for 0.3 microvolts or 0.5 microvolts, whatever it says in the manual. So this is way out of spec, you see. If you're not getting 12 dB or better at the spec that it says it should be, then the problem is you've got a fault on the receiver. Could be alignment, could be a fault, but that's just a way of knowing, and that's how you spec test receivers. Most radio receivers in the world, particularly FM, VHF and UHF, tend to squelch out and get very noisy at about 0.5 of a microvolt to 0.1 of a microvolt, and that's just the way it is with receivers. But if they're going out of alignment or they've got a problem, then it can take millivolts even, or many hundreds of microvolts for some receivers to open up. If we've got dry joints, an RF amp's gone down, a filter's packing in, and the VCO's off frequency, or the reference oscillator's gone off frequency for the synthesizer, the pin diodes in the antenna switch, or the relay contacts, if it's mechanically switched, the antenna between the transmit receive, sometimes relay contacts get dirty in radios and that can cause problems, or pin diodes can fail, you know, if a solid state switched. There's so many things, component failures that can go on in a radio, but that gives you an idea, you know, obviously of how to do that. Now, so that's the SINAD measurement. Obviously we can look at distortion as well, which is quite important when we're doing discriminator measurements. So we need minimal distortion at a particular level of RF, and so the distortion level on this is 1.5%, which is very low, 1.5. But obviously if this was corrupted, then that would be a very high level. So you would make adjustments in the radio's receiver discriminator section on the IF filter part, the IF stage rather, of the radio receiver. You would make adjustments to make that sinusoidal waveform as undistorted as you possibly can. And that's some FM alignments that you'll see me do on other videos as well. You can obviously, as part of this test as well, do tones, so you can then do CTCSS. So if you've got a radio that's got CTCSS encode and decode enabled, you can then put in the relevant CTCSS tones and test that. But as you can see there, and as well we've got scope bar chart as well. So again, we can see the AF level and then the distortion as well. Now, signal to noise, if I go back into AF filter, oh, where is it now? I put the speech band filter on, so 300 Hz to 3 kHz. We'll go to what is the distortion signal, and we'll put signal to noise. So that's pretty much like SINAD, so it's just a different way of measuring it. So as we adjust the RF level, so that's an idea there that, you know, some of them, these radio receivers prefer the signal to noise in the spec. They'll quote SN, particularly for AM, SSB receivers, or if for FM it's SINAD generally. So, you know, that's how you can do measurements with that. Obviously we've got the different AF filters as well, so you've got basically a 300 Hz to 3.4 kHz bandwidth filter, 50 kHz, 15 kHz, or a 4 kHz band pass. So that would include things like your CTCSS as well, and that. Obviously all your tone standards as well, POCSAG, DTMF, a sequential tone signaling standards, they're all there. And then under AF test, this is where you would do something different. So the RF signal generator is still working, so then you can go into further tests on AF tests. You've got an audio gen on the output there. Again, it's pretty much like what we had on the receiver test, where you can set up, you know, the similar test circumstances for receiver testing. So that's part of it, if you like. But the audio test is really useful for measuring AF filters and AF amplifiers, for example, between those two ports. So it then allows the test set to be used in audio repairs, particularly useful for microphone audio amplifiers, AF power amplifier stages in radios, and audio processing testing of system boards and options that are fitted to radio, such as CTCSS, encryption boards, DCS, things like that. You can emulate quite a bit out of these two ports by generating signals out, as well as getting them back in and analysing them. So you can test audio amplifiers, all sorts of things like that as well, so that branches out into that. So we'll have a look at the spectrum analyzer again now with the track gen with a filter, and then we'll have a look at that feature as well. Okay, so we're ready now to do a tracking gen measurement of this filter, and have a look at that. So we've got some cables already connected up. Obviously we're going to use a port to send a signal out on and a port to receive a signal in on, which we'll set up. We've just got some cables connected. Before you do any measurements using a tracking generator, you must always connect the in and out together, so you need to calibrate the lead losses. Now when we go on to the spectrum analyzer function, there's a track gen option here, so we can enable that track gen, and then we've got Rfgen on and off track gen. So now we've got the track gen, so we need to make sure that those, if not already, these LEDs need to be in this fashion where we've got an input port and then an output port. What we need to do as well is we need to set the start and stop frequency, but before we do that, if I just look at roughly what the filter is, it's UHF. Sometimes you don't get labels on them that describe the frequencies they operate at, so you just make the span very wide, you know, the start and stop frequencies. So we've currently got a start frequency here, let's have a look. It says 0 Hertz. Well, I'll make that something like 300 megahertz, and then a stop frequency of 500 megahertz. Now we set the stop and start frequencies up, start and stop. There. We just now need to get the signal generator to work and for it to start doing its tracking gen. So that's the track gen on. We've got a level here. Ideally we need to calibrate the Rfgen level now. Level to 0 dBm. At the moment it is minus 21 dBm, so that's the level of signal that's coming out of this port here and leaving to come back in on this port. I do want to set that at 0 dBm, and it might disappear off the screen, but that's fine, because then what we can do now is when we go back to here, we can then use the level up and down to bring that line down. Now if it's above the top line, depending on the spectrum analyzer mode, at the moment this doesn't have a normalized feature on this spectrum analyzer, where unlike the HP Agilent spectrum analyzers, they have like a normalized mode. So once you set the track gen up and everything and its levels, you normalize it, then takes into account the lead losses and cancels them out, because it adjusts itself. But if you want 0 dBm out, it makes minor changes in the adjustment to make sure 0 dBm comes in. So it factors in the losses in the cables. That's why you join them in the middle. This spectrum analyzer doesn't do that as far as I'm aware. Basically you have to do it manually. So if you want, for example, 0 dBm on this top line, or this line here, we've got it minus 10 dBs below the top line. So if you want it dead on the top line, then you can adjust the reference level, and then you can then get it onto the top line, then adjust the Rfgen level to then get that line just at the start there on that 0 dBm point, which is the top line. So that then will give us a total system loss of the cables as being 0.8 dBs. So the entire system loss, you see, for those coaxial cables we're using in this measurement equates to 0.8 dB. Because we're setting our Rfgen level coming out at 0 dB, and then obviously it's higher than the top line at this stage. So with the losses, we've calibrated now to the top line. We've got a 0.8 dB loss between the inner and outer of these cables. So between the sending out and the receiving in cable. So depending on the length, obviously you need as short a length cable as you possibly can. This microwave coax that I'm using at the moment, there must be about 3 meters on this. So considering 3 meters at UHF and only getting 0.8 dB including all these connectors, that's pretty good. So we're currently tracking between 300 megahertz to 500 megahertz. So now we're ready to connect these coaxial connectors now to the filter. So what I'll do now is I'll unplug this BNC and connect it onto the side of the filter. And again, it's always difficult working one-handed, and these cables are quite stiff as well. They're being microwave coax. They're like memory. They remember where they've last been coiled up, and they try and recoil themselves, so it tries to drag things off the table, which is never good. And then of course we will reconnect up. I think I've got the right, oh yes, I've just got to unplug that and get the shouldn't really turn the body of the plug, but you should turn that part, but I'm doing it for quickness. Likewise, when you're connecting back, it should be the this part of the plug that you're turning rather than the body of the plug, because it can erode the connections. Right, I've dropped it on the floor, so I'm going to have to connect it all up off camera, and I'll come back to you shortly. Okay, so we've connected the filter up now, because things dropped on the floor as usual when you're trying to work one-handed. And so we've got, you know, our ports, our tuning cavities here, and this is the frequency response we're getting. So if we have a look at that a bit closer, so the center frequency according to this is 400 megahertz. So we can always change the center frequency by moving the rotary control, and then we can look at the center frequency there, which is 416.6 megahertz. So does that equate to what that says? I think it does. 416 point whatever it is, 0.25 megahertz. So if we decrease the span from 200 megahertz down to say 10 megahertz, we should see more of that response. So obviously this is the centre of the waveform. It seems as if it's a little bit shifted that way to the right, just slightly. It's not exactly bang in the middle, but that's 416.6 megahertz. It said that the centre frequency that this was tuned at was 416.25. So I'll be interested to see what that'd be like with 25 megahertz. Then let's have a look. Let me just change the centre frequency. Yeah, 25 megahertz is there, so it's near as damn it, you know, just adjust the level. So, and then we've got the marker. Marker minus 4.5 dBm. Let me just go back up there. So it's only got like a 0.5 dB loss then, as we're denoting here, 0.5 dBm loss across that filter. Because if you remember, we connected the input and output cables together, and then we calibrated the instrument so that what we were getting back in was 0 dBm. So now we've reconnected to this filter, and now it's giving 0.5 dBm. It means that's what the loss is across this filter. Half a dB, which is quite good. So if we open the span up again to say 20 megahertz, and then we can see the bandwidth. Now some spectrum analyzers allow you to calculate the bandwidth for 3 dB points. They'll then give you the bandwidth of the filter. I can't see that on this particular test set. There's only the Rfgen, the marker. Might be able to calculate 3 dB points from there. I'm not sure if that's the delta marker, but you'd have to look at your 3 dB points. So that's 3 dBs there. So that's 414.65, and then you'd have to then go up then to 3 dBs again roughly. Just get it finally done to 418. So that will be its bandwidth, where we were to start with to there is its actual bandwidth. Now other brands of spectrum analyzers that are just solely spectrum analyzers, obviously, have far more functionality when it comes to the refinement, such as calculating bandwidth, delta markers. You can obviously increase or decrease the resolution bandwidth. You can the dynamic range of the instrument as well can be adjusted so that you can get right down below neg 100 dBm in the noise floor when you're doing duplexers. So there's all sorts of extra facilities and features that you get with a spectrum analyzer like this. But when it comes to most radio test sets, the spectrum analyzers are good, don't get me wrong, but they're not as refined as a dedicated spectrum analyzer would be. But that's quite adequate, that, don't get me wrong, but it depends what you're wanting, what measurements you're doing. Most people are just wanting to tune duplexers or filters, band pass, band stop, band reject. That kind of instrument is fine for doing that, but when you're getting into the, I wouldn't say advanced side of things, but when you're really getting into things like measuring phase noise, looking at delta markers, accurate measurements of signals and bandwidth and phase noise measurements, things like that, you really need a dedicated spectrum analyzer on its own for that. But that's perfectly okay, that for using with that. But at least you've seen how the tracking generator is used on the 2945, and might give you confidence if you get one of these to be able to do things yourself. You've just got to be mindful that you select the appropriate input-output port. You can have it in any configuration you want. Obviously you can't set the test set up so that both LEDs are on here for a track gen, because it will just be picking itself back up. So you need to have one port isolated from the other, one for in, one for out, whether that's those two, or those two, it's up to you, but it can't be all on the same port. You've got to have two different ports. So you remember that, you'll be fine. Because despite that, it does allow, the test set does allow you to select the same port, and then you start making, well, start preparing your measurement and making all your adjustments and settings, and then you think something's wrong, I've done something wrong, and then you forget about the fact that you've got to, you know, obviously put the in-out port on. I think it does, once tracking gen's enabled, I think it stops you from being able to select the same port, it does. So there's a bit of a lockout feature on it, but you can cause yourself a bit of an issue when you go between different ports. They have different attenuation levels, different sensitivities, and by selecting different ports you get different responses with the levels, because obviously some ports are more sensitive than the others. So again, that needs to be taken into account when you do your calibration, your measurements. So that's it really on that. Okay, now just a quick run through the internals. Rather than strip down the one that works, I've got my spare one out here which I use for spare parts. Keep it back for doing, you know, obviously board swaps, things like that. So yeah, the regard to common faults now, the type of problems that you get with these, particularly now age related, the LCD module is one of the main failures on these units. If you ever buy one of these and there's lines in the display or whatever, it's a sign that the module's failing. What that generally is, it's like an elastomeric connector that's glued on the display drivers that are on the board, which goes on the back of the LCD module, and there's a connection between there and the LCD glass, and so therefore the X and Y pass for the pixels, if you like, for energizing the pixels, get interrupted because these minute electrical connections that are glued onto the glass at the side start to deteriorate. The glue dries up and it allows the flexi to come away from the glass, and so you can do fixes on them, but you need some specialist gear if you haven't got the kind of equipment that I have, where you can heat up that strip to the right temperature and try and re-glue it. Sometimes it works, sometimes it doesn't. I get a lot of them where the people have made some severe problems, even worse, by trying to fix them and put too much heat on and melt the flexi and things like that. But the LCD modules are swines. You know, so that's the main problem with them, is LCD. It's complicated further by the fact that it doesn't have an external VGA output or composite video output. So even if a display was stuffed, you can't sort of use a secondary monitor to display what would be on it. They're very hard to get hold of now, as the LCD displays. Extremely hard to get hold of. I think you'd struggle, to be honest, to get one now. Now, with regards to the internals, unlike the Marconi 2955 radio test sets, they use separate modules and separate system cards for doing the various elements of the test instrument and its capabilities. On these test sets, it's not like that. They've gone away, and it explains this in the service manual, of doing component level repairs on some of the boards, and that makes fault diagnosis even more complicated. Fortunately, they have included all the diagrams in the service manual for all of the instrument, but insofar as doing component level repairs, things like the RF attenuators and other boards, they don't recommend doing that. They recommend replacing the board, so that makes servicing more complicated. This is the analog board, basically one of the analog boards anyway, which I'll show you the others in a moment. But basically what they've done, they've got different sections. So for example, the AM section is here. That's the FM section for what would be the transmit monitor. So when you're transmitting a signal into the N-type on the front, that it would then demodulate the AM and FM in this section. We've got the audio amplifier stage. That's the TDA chip for the AFgen output, which is fed out on the AFgen out here. Then we have we've got some processors with some software. The common faults that we get on these boards are these electrolytic capacitors that are mounted on the board, which fail, unfortunately. These types, mainly the 6.3 volt 100 microfarad, which you get on different versions of these, are scattered all over the place. They mainly leak and cause issues. Now this board generally doesn't have too much of a problem, because the IF comes in here on a socket down here. That connects in there, and that connects the IF to the relevant stages. Your adjustments for calibration is done two halves. Software related, where you access the Calibration Diagnostics menu for entering a secret code in order to break into that, and then you can then do software related calibration adjustments. Likewise as well, and they are labelled on the pots. It does tell you, for example, like down there, it'll say something like FM level, AM level, things like that. It generally tells you what they are, these pots, when you're connecting your test probes up to the test points. It's well laid out, it's well thought out, to be honest, and you can then adjust these potentiometers for certain analog measurements. Now, on the other side of this instrument, basically, this sits here on the top section, that analog board, but then we have another analog board just here. Obviously this is a power supply, another common failure. It's a modular power supply. It's not designed to be repaired to component level, but I've repaired plenty of those. I just held on with a couple of screws at the back and it comes off. It's fairly easy to get to. Underneath this top tray is where we get into the nitty-gritty of things. We've got two lots of RF trays on this, one at the top and one at the bottom, which I'll show you in a moment. But basically this is where we have some option boards, such as the SSB option goes in this can here. We've got the local oscillator synthesizers, we've got the logarithmic amplifier, the log amp, RF amp stages as well for the RF signal generator, and quite a lot of the spectrum analyzer processing is done on this side as well. And I have got boards out of this, which I've put to one side. This here is where most of the problems occur. This is the digital signal processing board and processor board, and basically one of the common problems that you get with these is the bar charts as well, where they don't display properly. You'll be receiving a signal on the oscilloscope, it'll look perfect, but the bar charts, one will be like that and the other will be constantly extended out. It's as if it's only measuring 1/2 of a sinusoidal wave, so it always looks like the mod's off, and that'll make it fail its self-test, particularly on FM deviation and AM mod and AM depth. And it's these two capacitors here. The digital signal processor on this instrument for the analog functions, for doing the bar charts and also the oscilloscope, are done by basically two chips. This chip here, which is a digital signal processor IC, that's an 8-bit DSP, where it takes analog in and outputs 8 bits digital. And likewise, one of these two is again another signal processor, where it deals with for the oscilloscope. Now the technical description is a little bit misleading in the fact that it says that one of the DSP chips, which is one of these big ones over here, actually deals with the bar chart, which it says there, the bar charts. And although it does do that in the DSP architecture, it doesn't do that directly, because basically the oscilloscope input comes into one of these DSP chips via a test point, and that then produces the waveform on the oscilloscope. However, the DSP chip also deals with the bar chart, but not directly, because if you disconnect the audio to the DSP on this side, the bar charts still continue to work, or work inoperatively, whereas the oscilloscope stops working when you disconnect the audio to this processor. So what it does, it uses this from the log amplifier, and the signal to noise, the bar charts and everything are all through this DSP via these two electrolytic capacitors. There are two summing amps that convert the audio signal into a DC bias, which then represents a level via the DAC in this digital processor, to then give you a graphical example on the bar charts on the display. So if one of them's stuck out further than the other, it's one of these electrolytic caps which is which is a leak. So if you replace those caps, generally sorts out the bar chart issues, with one bar chart being longer than the other and out of cal and failing self-tests. The 8-bit data from that is fed to the DSP, and that then, if you like, combines the oscilloscope and bar chart functions together, plus other measurements, digital signal processing as well, to output signals from there in order to generate signals for the output, the audio side and what have you. There's software fitted to these sockets as well. They are common with dry joints as well to some of the ICs and the sockets. A lot of resoldering work needed on some of them, and that's revealed by spring circuit freezer, and then suddenly it goes off or it starts doing weird things. Mainly electrolytic caps though leaking. I'm afraid you'll have to blanket change all the electrolytic caps, and that then will normally get rid of a lot of the issues that there are, particularly with some of the faults that appear in the self-test side of things. Not a lot of other component failures, to be fair, apart from capacitors and dry joints. Not really had any major problems with any of the ICs, apart from some of the dry joint problems can be quite widespread on some production boards and different variants and versions. But basically the DSP and oscilloscope functions are the ones that tend to be the most common. Obviously on the other side of the instrument as well, if we have a look there, we've got a processor board again here, a microprocessor board, which also is an ancillary to the board I've just shown you. There are two processors, one on each board, which share the data bus between each other via the data bus cables that you could see, the multi-core cables. So they share some of the system functionality. Options that are fitted, like this is an option here. I think this is a 600 ohm option, or a Cellular Systems option board. I'll look at that at some other point, I think, and find out what that is. options are fitted in this area a lot of the time, and then there's an RF tray underneath as well, which I'll try and get into in a moment. But basically all your signal generator attenuators, switched in and out attenuators, which are non-serviceable, I'm afraid, on this instrument. I do repair them, and I have managed to do repairs on them. They are very tricky, but you can't get parts for them, and they're not designed to be repaired, and there isn't a schematic diagram for them in the service manual because they're not intended to be repaired. So that's another thing. If you get them with faulty RF attenuators on, it's down to improvisation and that aspect of it. Again, this tray hinges out to allow you then access to the RF boards underneath. So it's like a sandwich all the way through. So that's, you know, it is built to be serviced. You know, you just slacken 2 screws off and the boards hinge back and what have you. So that's about it really for the internals. I think we've done the power supply already, and the front panel is quite easy to get off on them, unlike other test sets. You've just got the screws on the side up here which allow the front panel to be removed, and then obviously to get to the LCD display. Now the RF attenuator on this one is slightly different to what it is on other radio test sets, and you have to be quite surprised at just how small it is. But the 150 watt N-type RF attenuator is this little unit here, and then obviously there's a 20 dB pad in there, which then gives 20 dB attenuation. Now what happens is with these N-types can get quite hot when you're transmitting into the test set for quite some time at high power. This unit heats up quite a lot, and because it's machined and fastened to this N-type, it means the connector gets quite hot. I wouldn't say it can burn your hand, but it can damn near do if a transmitter's doing so 40-50 watts for 10, 15, 20 minutes or whatever into a N-type, if you're doing some kind of, you know, testing, soak testing on a transmitter. Although it is bolted to the chassis and it's meant to heat sink off, it generally does that at a slower rate than there. This heats up quite first, if you like, than the rest of it. These can take a few hundred watts easy of RF power, 150 watts continuous, but it can take higher RF levels. It has got a thermal sensor on it, so that if it does get too hot, it will come up with an RF overload warning on the front. But that's about it really. It's got this funny coax that, if you've got to be careful when you're getting this in and out a lot, this tray, or disconnecting these coax. Okay, if you bend it too many times, it will snap. So you've got to be very careful with this coax. It's soft. It's like lead. It's soft. It's not rigid. It's sort of semi-rigid. So you've got to be careful not to break that when you're looking at it. So that's that really for the internals. Okay, we've got the underside off now of the unit. Just wanted to show you where the option boards fitted for sideband, if the unit's fitted with it. Before we do that, what you have to do is you have to remove this tray, which has got one of the ancillary microprocessor boards on it, because this is a microprocessor board, and there's another microprocessor board on the other side, which I've shown you earlier in the video. But basically this tray removes first, so that has to come out first, and then what basically happens is this then reveals this screening can here, which if I can just get rid of that onto there and have a look at this now. Now that screening can has got quite a lot of screws in it. It goes basically over the entire assembly, and you have to remove all the screws. It's not too bad a job to do, but once you've done that, just have to label up these cables that connect to that processor board we were looking at. And this, be careful not to pull the cable on the plug, otherwise you can pull the back off the plug and the wires come off. I've had quite a few of these test sets in years past where people have sent them for repair after they've had a go to me to have a look at for them, and they've actually given up on it, fault finding process, because they've caused another fault by yanking on this cable which unplugs from the processor board I've just shown you, and by doing that it can pull the back off the plug just slightly, enough so the wires become disconnected. I've had to repair a lot of those in the past, and it's a little problem that they have these, especially as they get older and the plastic gets brittle. Now underneath we've got obviously the RF attenuators for the signal generator section, final output RF amplifier. This is also a pad, switch in and out pad for the transmit receive side as well, an optional additional pad that's above and beyond what's provided here. We've got other modules installed, but then basically what you've got in this bottom corner here, where there's this big empty space, this is where the SSB A15 board, it's called, that's the optional extra that's fitted to these if you have SSB demod on them. So if there's nothing there, like in this case, this isn't fitted as an option. So you might be able to select it in the menu on the front panel, AM/FM SSB, but when you select SSB it won't demodulate anything because naturally it's board's missing. So that's fitted as an option on these that you have to pay for. A bit like GPIB, that's fitted as an option as well, and likewise there are other options on this test, like 600 ohm interface etc, that's fitted, but they've got option boards all over the place on these. But that's just an overview of the underside of the unit, and that's where the SSB receiver would live if it was there. So that's that. So it's just a little selection of some of the boards that are in the RF tray underneath, and we've got various synthesizer boards. Again, leaking capacitors commonplace. Again, more synthesizers, 90 megahertz local oscillators, and such like. We've got the RF switcher board here, which switches between the two antenna sockets and obviously the N-type after it's been reduced in power by 20 dBs. Now these do suffer occasionally with defective relays, mainly these types. These don't look like they're RF relays, but they actually are. What they are is a plastic covered metal canned relay that are the latch-in type, where once you give them a pulse of DC on the coil, it latches one way, and then you give it another pulse on the coil and it latches the other. So the sort of not like conventional relays where the coil needs to be energized all the time. These silver cans here are Teledyne relays, and these are very expensive to buy normally. If I zoom in and see if I can get some detail on that for you, but I think you can see that it says Teledyne on it, if we can get it to, and it shows you the relay configuration. Just wondering if I can get that to shine in the light a bit, but basically it's a Teledyne relay. Now they're very rare, those RF relays, and so they're very useful to keep as spares. But these relays are proper RF relays as well, and they are screened and metal canned, and obviously we've got quite a few connections underneath them, and for coaxial switching. So you do get problems with the relays from time to time, and you also get problems with the RF attenuator section needing to be taken apart and cleaned and then reassembled again. So yeah, I think that's about it really, as much as I can say. There are obviously just the same faults on these you get with any other test instrument. There's nothing different really. It's just a matter of just reading the service manual, which is quite well written, just to trace faults down to component level. You can see on this board it's actually been reworked as well. This processor, or this chip here, has been reworked, so there's quite a lot of dry joint issues on these I've had, and you can tell that Marconi have had them back as well in warranty and done resolder jobs on some of the test sets that haven't been opened since factory. So yeah, it's a common problem. So yes, I think I'll show you the calibration menu, I think, on the test set, and I think that should be about it, really. Okay, well, we're joined by the technical manager now, who's come to give us guidance on doing the diagnostic calibration mode. And basically, to access the diagnostic calibration mode, you press the help setup key, and then within the help setup key you've got these two features here, which are diagnostic and calibration, and they both say locked, obviously. Now, one of the warnings that I want to give people before we go into this is that once you go into these modes, it says quite clearly in the manual, and it is absolutely clear in there, that if you were to go into these menus and start tinkering with things that you don't know about, there are software overwrite facilities in there, particularly to do with the serial number, model number, also the features of the test set as well, software, firmware, all that can be accessed through these menus. Now, what it says in the manual, although I've not had experience of it myself, because I obviously don't mess with things that I don't know, is that if you were to faff about with it and you get something wrong, it will basically write the test set off. It'll screw the firmware and software in the test set, and you won't be able to recover it. And it says the only method then is to return the instrument back to Marconi Instruments for the software to be put back on the test set. And it does warn you quite clearly that you will perform irreversible damage to the test set if you start faffing about with the software settings and things like that in there, and you won't recover it. It's very clear on that. So if you do go into this mode and you start doing things that you're not really familiar with doing, then you can cause severe damage. Now, for that reason, and to protect people watching this video who want to have a go but yet don't want to read the service manual and don't want to know the technical background before performing these measurements, there's a very clear procedure in the service manual that tells you how to go about doing all these alignments. Now, if that's not followed, you will damage the test set and you will not be able to recover it. So for that reason, what I'm going to do, I'm going to omit to show people, although we're going to go into these menus and we're going to look at what's in them, I'm not going to show the code to unlock it, because that code is actually contained in the maintenance service manual for this radio test set. It's in all the different variants of print of the IFR 2945 radio test set service manual. And I'm doing that because there are people out there that no doubt watch this video that's have got a 2945 that's got a minor problem on it, for example, and they'll watch my video, and if I were to reveal that code, they'll type it in and they'll start messing with it. And then unfortunately, because they're not reading the service manual and not taking note of the procedures within that manual, you will damage or break your test set, and it'll be a write-off, and you'll have to throw it out or sell it for parts or whatever. So to prevent that from happening, because you can edit serial numbers, firmware, software revisions, options, you can do all kinds of things in these menus that you know can cause severe damage to the test set if you mess it up. So what I'm going to do is I'm going to lock the menus, we'll go into it, but if you're serious about doing any alignments or calibrations yourself on the 2945, then by all means read the service manual, and the unlock code is in the service manual under the alignment procedures, and that way then at least I'm confident in myself of when I do this video as an educational video for those who are interested in doing maintenance and repair on these, that I know then you're following the procedures within the manual and not trying to sort of wing it yourself. So we'll enter the diagnostics code in now, and we'll then go into it'll unlock both menus, the code that I'm going to put in. So we'll just move away so you can't see the secret code. Right, so we've entered that in, and we've got both menus unlocked. Now when you're in these menus, if we look at the diagnostic first, within the diagnostics mode, you can actually you've got things like, for example, the I/O memory, clear non-volatile memory, clear the clock, execute trace, you've got diagnostic enable as well, cell fail, and then you've got obviously B1 setup. Now B1 setup is quite a common adjustment, because within that you set up, when we were talking earlier about the internal adjustment pots inside, which you'll see in the earlier part of the video when I looked at the internals of the instrument on the analog board that sits at the top here. The potentiometers that are on that board are adjusted in accordance with these menus. So you basically go into one of these menus for setting, say, AF level, and it will set up a test within the instrument, which then you'll obviously use the I/O ports in synergy with external test equipment such as DVM, SIGGEN, audio generators, oscilloscopes, and using the test points internally within the instrument via these menus, you will then adjust those potentiometers, those blue pots, and that will then set the levels perfectly then, and then you'll advance on to the next test. Now it's very important that you follow the manual, because some tests, it's a domino effect, have to be done before others, otherwise it'll affect the other tests that you'll be doing. So that's worth remembering, not to try and jump tests and alignments. There's quite a lot, there's hundreds of alignments to be done on these test sets. As a matter of fact, on the RF SIGGEN, I think there's somewhere around about 340 calibration points throughout its entire frequency range, and that's just on the SIGGEN alone. Multiply that by the TX power meter, narrowband and broadband, the mod meters for both AM and FM. You know, you could spend over 2 days calibrating this, you know, if you do everything on it. So that's why you've got to be so careful. But as you can see there, we've got not just the AF levels, we've got scope, AM level, FM level, RF level, mic level, which is obviously when using the accessory connector. Likewise, you can clear the non-volatile memory and set the IOs and what have you, execute trace, diagnostic enable. So when you're in that, that allows you then to do certain trace features within the instrument as well, to fault find within the instrument as a fault finding aid. Under the Calibrate screen, when it comes up, you can set the output level of a signal generator, the linearity of the output amplifier, the RF amplifier, the attenuators, you can set those up, the AM level, the FM level, because obviously the other screen was for the signal generator side of things. You can also set up the transmit monitor AM and FM level as well. The 2-port power meter, so it's basically calibrating these BNCs and N-types power meters. We've got obviously a 1-port power meter as well, which is for the N-type, whereas that's for the BNCs. We've got obviously frequency standard calibration, narrowband power meter adjustment, store calibration, and then return back to the previous menu. And so, you know, you can do quite a lot of adjustments in there. Now the way that the test set will save its calibration, after you've obviously selected save in that menu, these remain unlocked until you turn the test set off. So when we're in the diagnostics mode and you've done your calibration, then you select, say, store cal, but then it's still not saved to memory permanently until you switch the test set off. When you switch the test set off at the back, okay, it stores everything, or it has stored everything to memory at that point. When you turn the test set back on, those menus will be locked again, obviously. So we'll flick the test set back on. Now when you're back into the test set, if you go back into the help setup menu, they're locked again now. So that's basically how you perform those calibrations and things. Now the procedure for calibrating these is no different to the other Marconi radio test sets really. You just follow the instructions in the service manual, and then you will, providing you follow step 1, 2, 3, 4 in sequential order right the way up to the end steps and do the whole instrument, then you're fine. Where you get a lot of problems with these is when people are impatient and they try and do calibrations that are not in sequence, and it does tell you in the manual that you need to perform certain steps before others. So You know, if you just want to calibrate the AF section, for example, for the Rfgen, that can be done without calibrating the whole instrument, for example, and it will tell you that in the service manual as well. Now, the calibration procedure in the service manual is very well written. It's a very self-explanatory procedure, but it is to be followed rigorously by the manual, because if it's not followed, you will damage the test set. And I have seen examples where I've had test sets where they have done that. They've damaged the test set by clearing out the memory and corrupting the software in the instrument, and basically I've had to you know, I've got a data 48, a data man programmer, and I can also do some of the processor memories as well. I've got the sockets to put the processors in, and obviously recover some of the software elements of them by copying the memory maps. But you know, by no means am I an expert on the whole Marconi memory map system. So you know, obviously you've got to be very careful what you're doing, because once the software's been wiped off it, that's it, you know, and the firmware's gone, you're pretty much written your radio test set off, or you'll have to buy another processor board with the chips on it. Now, this is a calibration procedure. It tells you about how to get into the calibration mode anyway at the beginning of this section, but it tells you about the output level, for example. They're setting up the output level, on how to follow that procedure, what to connect to what test point, what to adjust. It talks about the attenuators and what to select, because you have to do like a pre-setup as part of the setup diagnostic procedure on the instrument. You have to set up certain attenuators in a particular order before then you do the calibration. So you've got to really follow all these numbered steps precisely, otherwise you'll end up causing yourself, you know, more problems than you started out with. And that gives you information there as to how to set up the different parts of it. So this is just a quick go through. You can change the serial numbers on the test set as well. There's another code which again is in the service manual that you enter in. So those serial numbers there, this is just a one I put in, and you've got your software version numbers as well, which you can change yourself. You can put all those in. So there's a lot that you can do with it, and you can obviously add and remove systems as well. Now, again, under systems, they come standard with certain features. Now, if systems can't be selected, you can enable them by entering a code in. Again, that's in the manual as well, the service manual, about how to do that. But basically, say if MPT 1327 was in the list but you couldn't select it when you press the button, like I've done here, I've disabled these. You can re-enable these by entering a secret code in, which again is in the manual, because these are all fitted as part of the software on the instrument. So you just physically enable them, re-enable them, turn them on. So you can do that if you want to do that. Again, some of the signalling standards that are used in here will need adjustment in the analog board on the test set, because obviously they're producing different signalling standards, and if the options haven't been previously enabled, then there are some analog adjustments to do on the B1 board, which then will set up the levels correctly for those signalling systems. So yeah, that's just a little rundown on the calibration diagnostic and system menu. But again, it's mainly all through software that you do these changes, and then once you've done them, then you know you can just calibrate the instrument properly and then save the calibration. Once you've done, then it should have saved it, and you'll be able to use the test set as it should be. And finally, of course, once you've done your calibration sequences, etc., to check that the adjustments have been done correctly as well, if you go back to the help setup menu, and then go back to self-test. But before you do that, really, it's always better to do memory, and then you've got 0, 1, which is a factory default, factory reset. So 0, 1, okay, and then you can then go to help test, self-test, and then run the go. Now it should pass all the tests. If it doesn't, then you've done an adjustment wrong, you know, in the analog measurement side of things. But it should pass them all without issue. But be aware that if you don't press memory 0, 1 to recall the factory default settings, then it can fail on certain tests because you've set the instrument up differently prior to running the self-test. Like I explained earlier in the video, on some software versions or some revisions, they've made it so that when you go into the self-test, it presets the instrument to the factory default before allowing this to take place. On the older software versions, if you're in a different mode, say for example you're being in the spectrum analyzer and you set the track gen up or something like that, and you've got different ports on here, when you go to self-test it'll start failing things, and that's because it's not being defaulted to factory default settings. So before you go into any self-test routine, just do the memory 0, 1 to recall the factory default state, and that way then it should pass the self-test. Obviously if it doesn't, you've still got a problem that you need to resolve, but providing you follow the information in the service manual, then you shouldn't have a problem if you do the adjustments correctly. Yeah, so as well as that, if you're doing any board replacements, for example like the microprocessor board, it tells you there about what to do. So for example it says the EEPROM, the electrically erasable programmable read-only memory, IC32, which is on the microprocessor board, which is what we showed you earlier in the video, contains all the options information. So all this options information here, it's contained there, the serial number and the calibration data. And it says if IC32 can be transferred from the new PCB, then no other adjustments or setups are needed. If it cannot, then the new board must be configured for use with a particular instrument. It says that the replacement PCB supplied contains no serial number, so that'll all be zeros. It says to enter the serial number, the instrument proceed as follows, which is then obviously entering in the code that I mentioned earlier, and then to change the serial numbers. It says though, and this is where, you know, this is just one of many warnings it gives. Caution, the following key presses enable a hidden diagnostics menu. Once in this menu, do not press any other keys other than those stated below. Incorrect key presses could seriously affect the calibration and operation of the instrument, may result in the unit having to be returned to the factory for reconfiguration, software programming and firmware programming and realignment. So although there's a diagnostics code to get into here that you enter in, and to unlock these two menus, there are other codes which is again in the service manual that you enter in sequence on the keyboard here, and they then get into further hidden menus within the software environment of the instrument. Now if you were to mistype on the keyboard, you can screw the test set big time. So this is why you've got to be really precise, very careful when you're doing those measurements. You've got to be absolutely 100% attention to when you're typing these keys in, pressing these keypad, because if you press the wrong digit, then you can wipe other parts of the instrument's memory or software, corrupt it, and then once you've done that, that's it. And I have seen that happen. So you know, be aware of that, be very aware. That's why I've decided to not show the unlock code, because only those that are seriously wanting to do a maintenance or repair process on the instrument and recalibrate it would need to follow the guidance in the manual in order to get that information. So that's why I've decided not to show that in the video, what the code is, but I hope you understand that. It's for a very good reason, because other instruments that I've done repairs on this channel, although you can, you know, screw them up, you can recover them on other instruments. On this instrument you cannot recover it. I want to be absolutely clear about that. Once you make a mess of this menu, Calibrate menu, that's it. The instrument's written off. Unless you can get a replacement board to go in it, you know, you would screw the test set big time and regret ever going into it. So that's why I've decided to do what I've done, and I think you'll agree that by following the procedures in the maintenance manual to the letter from A to Z, then you can't go wrong. So I think in summary really it's quite a well-rounded radio test set. I mean, it's quite a nice size instrument. It's quite clever with some of the features that's on there. I think this is one of the reasons why the communications regulator in the UK, Ofcom, chose to purchase these over other instruments, because they had the so many features on there. Not just the transmit, receive, duplex, spectrum analyzer modes, but within the spectrum analyzer mode then you've got the track gen capability, the look and listen, off-air monitoring facility as well, which is great. Within the TX monitor as well, as we saw earlier under TX power, you've also got the harmonic analysis, so you can measure the harmonics, which we looked at earlier, and then more importantly, particularly for radio investigation capability, where you're tracing RF sources to a location using DF gear, and also looking at a particular noise source or a RF interference source. This test set is on par really with some of the really high-end perhaps Roden Swartz equipment and other manufacturers that do have this transient analysis, so you can then obviously monitor the signature of a transmitter. And that's what the communications regulators found very useful, is the fact that, you know, if I key up now on this, for example, and it finds a TX frequency, and then we enter that in, if I now go to that transmit analysis under TX power, transmit analysis, this would give us the signature of a transmitter, and obviously by using the attenuators as well, so I can, for example, adjust the reference level so it's a higher level, for example. Let's have a look here. You can increase the arming rate on both the leading edge and falling edge of an RF transmission as well, so you can get detailed information of a unique signature. Now every radio transmitter has a unique signature, so this start of the transmission is unique, and you can store these traces as well, and likewise as well you can also do it on the falling edge as well. So I'm keyed up at the moment, I unkey, then it will give a signature of a falling RF, and that's unique for every radio, and that's obviously you can set it up a lot more than I've just shown you there, but basically when you do that, you know, you can capture all this information, and you can pull it in and pull it out, and you know, you can get as much information as you want on the transmit source. So that's a very good feature, that from a radio investigation point of view, in tracking down interfering RF sources, and also doing analysis of pulse transmitters, for example, which is obviously what it's used for in another capability, where you've got a pulsed radio transmitter such as a radar, pulsed radar application. Then you can obviously use this instrument to measure the linearity of the pulse. Now, although the frequency range of this instrument only goes up to 1 gigahertz, if you use it in conjunction with a down converter from say 12 gigahertz or whatever frequency the radar's on, you can monitor that there as well. So there's quite a lot of applications with these test sets. And I think that's one of the reasons why, you know, one of the communications regulators here in the UK, well, the only regulator, chose this radio test set over the others, is because it was so versatile, really. I've certainly seen a lot of places in the United States use these as well. I think the FCC have them, and also a lot of police forces in the United States have bought these test sets because they have the P25 capability and they also reached into various other signalling standards as well. So worldwide popular, but very versatile, very good, high end. I mean, don't forget these were made in the mid 1990s. The service manual came out in 2001, the one I've got, the version. So I think they sort of went up to probably about 2003, 4, something like that. From about 92, I think it was, 1991, 1992, I think, when they started making these. So they'll have had like a 10-year production run, I think, and then before they came to an end. And then the 29, 65s and 68 series came out after that. So, you know, a very good little test set, I must admit. The only thing I don't like about the test set, after all said and done, is the fact that it doesn't have video output on the back, which is a shame, really, because if it did have a video output on the back, I think it would have made it a bit better, especially for doing presentations or you know, being able to convey that information onto a large screen for more detailed analysis of what you can see. Although I do like the LCD module, I think it's one of the better test sets out the whole of the world market when it comes to LCD screens for its age. This has the more clear display on than others that I've had in the past, and other brands of radio test set, including Roden Swartz. And I think the screen on these is actually quite good. It's just a shame that they are, with the age now, due to faults prone to the elastomeric flexi strip that connects to the LCD glass failing with the glue and that. But unfortunately, it's the way it is when, you know, test sets knocking on for over 20 years old. So really, in summary, I mean, very advanced for its day when it was brought out. Very expensive radio test set, and great flexible use of instrument, and it's more user friendly, I think, than some of the other test instruments. It's not as, you know, clumsy as other instruments are. So with that, I think that's the end of the video now. I hope you've enjoyed the video. If you enjoyed it, please subscribe, and there'll be more videos like this coming. So from me and the technical manager, thank you very much for watching, and we'll catch you in the next one. Bye bye.